Well, welcome to part 4 of 4 about ecosystem modeling and the century and descent ecosystem models. In the first part, we talked about general ecosystem modeling concepts. Second part, we looked at the century and daily century models in detail. The third part, we examined some descent results and discussed how carbon and nitrogen cycling feedback on one another in managed agroecosystems. And finally, this will help you with your homework. We're going to take some descent results for Weld County, Colorado from the paper I talked about in my last lecture. And we're going to compute net greenhouse gas emissions, CO2 equivalents of different greenhouse gases, and also look at some performance metrics for evaluating model results. So the top 5 greenhouse gases in the atmosphere are ozone, nitrous oxide, carbon dioxide, water vapor, and methane. And 3 of these are simulated by the descent model, and they can be used to calculate net greenhouse gas emissions from different systems. Direct greenhouse gas fluxes in soils. So we'll be discussing greenhouse gas sources, which is going to be a positive value. That's a greenhouse gas source to the atmosphere gains greenhouse gases. Or if there's a greenhouse gas sink, they'll be represented as negative values here. That's a net loss of greenhouse gases in the atmosphere and a gain of carbon in the ecosystem. So greenhouse gas sources include the loss of ecosystem carbon, such as the loss of soil carbon, like we saw in the previous agricultural examples, or, for instance, the burning of plant biomass. N2O emissions come from nitrification, denitrification reactions. Nitrification usually occurs in aerobic soils. It's the conversion of ammonium to nitrate. Ammonium is NH4+, nitrate is NO3-, with the release of N2O as one of the byproducts. Denitrification usually occurs in very saturated soils. It's the reduction of NO3- to a form of nitrogen that has less oxygen in it, and subsequently the microbes that perform denitrification can release N2O or molecular nitrogen. The production of methane, CH4, is also known as methanogenesis, and that usually happens in saturated soils. Greenhouse gas sinks, a gain in ecosystem carbon, such as an increase in soil carbon or an increase in carbon in tree biomass. This is called sequestration. Methane oxidation is actually when methane is oxidized to carbon dioxide by methanotropes. They use methane as an energy source or carbon source. And this reduces the impact of greenhouse gases in the atmosphere because methane is a more potent greenhouse gas than CO2, as we'll see in a bit. So net greenhouse gases are calculated as the difference in total ecosystem carbon. And total ecosystem carbon can be plant carbon, soil carbon, plus litter carbon from a previous time to the current time. So from time t-1 to time t. And then you add all greenhouse gas emissions, such as N2O and methane emissions, and subtract the amount of methane that is oxidized. But all terms have to be converted to the same common unit, and that common unit is CO2 equivalents, abbreviated as CO2e. Remember in your homeworks or your lectures about units conversion, when you add terms together, they have to all be in the same units. You can't add N2O and CO2 without converting them both to CO2 equivalents. So net greenhouse gas emissions in equation form is total system carbon C at time t-1 minus total system carbon T at current time T plus N2O emissions plus CH4 emissions minus CH4 oxidation. So when there's less carbon at time t-1 than at time t, that those first two terms, total system carbon at time t-1 minus at time t is a negative term. So that means there has been a gain of carbon in the ecosystem. It's pulling it out of the atmosphere, and negative is a desirable outcome if you want to reduce greenhouse gases. So to convert to CO2 equivalents, there are a few conversion factors that you're going to need to know for your homework assignment. And the first one's easy. It's converting carbon to CO2. So if you recall me saying earlier that in descent, for example, all carbon pools and carbon fluxes are in grams of carbon per meter squared, not CO2. And all nitrogen fluxes are grams of nitrogen per meter squared, not grams of N2O. So whenever we have just grams of carbon, we have to convert to CO2 by multiplying 44 grams of in a CO2 molecule. There are 44 grams of CO2 for every 12 grams of carbon. So carbon times 44 over 12 gives you CO2 equivalents. Below that, grams of N2ON, that's the same thing as just grams of N. That's just the way we say, we just are looking at the nitrogen that's in the N2O and not the whole molecule. So for every 44 grams of N2O, 28 of those are nitrogen. So if you have nitrogen and you multiply by 44 over 28, you'll get grams of N2O. And then to convert N2O to carbon equivalents, there's what's called a 100-year time horizon global warming potential. It's approximately 300 for N2O, and it might vary depending on what source you look at, but let's just say it's 298. So that means that for every gram of N2O is equivalent to 298 grams of CO2. So you have to multiply grams of N2O by 298 to get grams of carbon CO2 equivalents. On the right side is methane. So methane carbon multiplied by 16 grams of methane for every 12 grams of carbon gives you grams of methane. And then once you have the weight of the molecule itself, the global warming potential for methane is 25 times that of CO2. So grams of CH4 times 25 grams of CO2 equivalents per gram of CH4 is the grams of CO2 equivalents from methane. So for your homework, we're not going to be looking at methane, but it's here for reference because you might need, there's a very good chance you might need it in the future. We'll just need the three equations that are on the left side of this slide. Okay, let's look at a small piece of the spreadsheet you're going to be working with for your homework assignment. This is just some numbers, descent results from year 1870 on, and looking at total system carbon during that year and N2O emissions during that year too. So the total system carbon is meant to be in December of the year. It's at the end of the year. And the N2O emissions are the total N2O emissions that occurred in that year. And again, these units are descent units. So total ecosystem carbon is grams of carbon per meter squared. And N2O is represented as grams of nitrogen per meter squared. So we have some conversions to do. And let's look at the graph first before we do any more computation. So this is Weld County. It was irrigated for a really long period because it was close to a river. And it was native grassland converted to cropland. So the conversion happened in about 1881. And so the blue line is soil carbon. So it was around 4,300 or so for the native grassland system. And then when plowing began, it dropped pretty rapidly, and plowing continued for many years. So the soil carbon levels dropped to less than half of what they were in the native system. And then when fertilizer came about and plants got more productive and more residue was left behind, the soil carbon started to build a little bit. And there's 3 different crops here, so there's a lot of dynamics each year. So there's corn, there's sugar beets, and alfalfa, and each have a different amount of plant residue they leave behind. And alfalfa is a nitrogen fixer, so it's going to put nitrogen into the soil even when it's not fertilized. And then on the graph, the orange line is N2O emissions. Those are the right side. The units are on the right side of the graph. And over the 120-year period or so, N2O went up and down, depending on the crop. And then around 1950, when fertilizer was starting to be used, N2O emissions probably about tripled what they were previous to fertilization. And they varied year to year based on the crop also. So just look at 1 year. Let's look at 1881 because that's the year plow out occurred. And we want to compute the greenhouse gas budget for that year. So total system carbon at T-1, that would be, if T is 1981, then T-1 is 1980, or I mean 1880, excuse me. So we want the total system carbon from 1880 minus the total system carbon from 1881 plus N2O emissions, all converted to CO2 equivalents to get our net greenhouse gas emissions. And so for the change in system carbon, that would be 4,160 grams of carbon in the ecosystem in 1980 minus 3894 in 1981 to give a change of 266. So there was 266 grams of carbon per meter squared lost between these 2 years. And then to convert 266 to CO2 equivalents, multiply by 44/12 to get 975. So that's just the contribution from the ecosystem carbon loss. Now let's compute the carbon equivalents from N2O emissions. These are pretty small numbers. So the N2O emissions in 1881 were 0.102546 grams of nitrogen, and we have to convert grams of nitrogen to grams of N2O by multiplying by 44/28, and then we compute grams of N2O to CO2 equivalents by multiplying by 298 to get 48 grams of CO2 equivalents per meter squared in 1881. And so you add those 2 numbers together for 1,023 grams of CO2 equivalents per meter squared in 1881. And so this is just 1 year, and of course, for a spreadsheet, you want to put this in a spreadsheet and compute it for every year. And so that will look like this. You can actually use these numbers in this slide to check your answers in your homework when you do them. So I've outlined the calculations I just showed you by hand, and so you have to do that. You have to put an equation in these in column D, E, and F to compute these values. And also notice I began in 1870. I think your spreadsheet's going to begin a little bit earlier, but you can't compute greenhouse gas emissions the first year because you need to know what the previous year was. So we start computing greenhouse gas emissions in the second year of the spreadsheet. So you'll see sometimes in column F is the net direct CO2 equivalents. Sometimes they're negative, sometimes they're positive. They're really big when there's plow out, and they go up and down depending on what crop is being grown. And in the graph, the blue line, the solid blue line, is a graph of column F. The solid orange line that's kind of hovering close to y equals 0 is the graph of column E. Those are the CO2 equivalents of nitrous oxide emissions. And then the dotted orange or red line, which is pretty much right behind the blue line, is the change in total system carbon from year to year. This is a really dynamic system. It's a lot different than that example. Hamilton, Nebraska that I showed you earlier. It's changing, the system carbon changes from year to year because there's different crops being grown every year. And if you look at the graph, like, you can kind of see that there's more values that are positive than are negative. And so we would probably expect that the net greenhouse gas flux is going to be positive if you add up all these numbers. And so if you add up all the numbers in column F at the very bottom where the numbers stop, I computed in my spreadsheet 13,544. Your number for your homework will be slightly different because I think your homework starts in 1860 or so, but it should be close. And so that means that since that's a positive number, that this particular field that we're simulating was a net source of greenhouse gases from 1870 to 2003. And that the controlling force here, if you want to call it that, what's dominating the greenhouse gas signal is the change in soil carbon. The N2O emissions are relatively minor compared to the changes in soil carbon, or system carbon each year. I did want to say one thing I forgot to say in the previous slide. I've been talking about direct N2O emissions, and those are from the source where you're considering it. Like, so we're considering direct emissions from the soil. We're looking at the changes in soil carbon at that point, and the N2O emissions and the methane emissions that would come from that very point. An example of an indirect source of N2O is something that comes from somewhere else. So, for instance, if you have a lot of nitrate in your soil and it leaches out and it goes to another location, and then some of that nitrate in that other location gets converted to N2O from denitrification, that N2O in that other location would be an indirect source of N2O. So that's the difference. But for this homework, we're only be considering the direct sources. And the last slide, how do you determine if your model results are good? And the best way to, the only way to do it is to have observations and to have predictions that are paired with observations, so you can see how close predictions are to observations. And you can have, so say, from years 1870 to 2003, you have a column of predicted grain yield. And then for the same years, you have in your spreadsheet, you have a column of measured grain yields for the same year. So you have two columns. So you have one column P for predicted values and one column O with O values for observed values. You could create a scatter plot of these, of the P and the O values, and you could just in Excel easily add a trend line that computes the intercept, the slope, and the R squared. And so the higher the R squared, the closer it is to 1, the better the correlation of those two. And hopefully it's a positive correlation. Hopefully there's a positive slope, because you would want them to be positively correlated with each other. Another thing, there's some other metrics. So just suppose you had 100 model predictions and 100 observations to go with each model predictions. And so let's say N is 100. You have 100 pairs of, or 100 observed predicted pairs. Then you can compute some metrics. This paper, Johnson and Huberger, that you should have been provided, is a super reference. I got it many years ago, and I just keep it around because there's a lot of performance metrics in it that are used commonly, and it's a really good reference for them. So I suggest to hang on to that paper, hang on to that PDF. The normalized average error, or NAE, is the mean of the predicted values and minus the mean of all the observations divided by the mean of all the observations. So in this case, in a spreadsheet, you'd have to compute one value, the mean of P, one value, the mean of observations, and use those three values in this simple ratio. The mean absolute error, MAE, you would need to compute, or you could compute in a spreadsheet. So whenever you see that sigma, that summation sign, that means you have to add up numbers in a column. And so you would have a column of P's, a column of O's, and then you'd have another column, which is the absolute value of P minus O. And then to get MAE, you would add up all the values in your third column and divide by the number of pairs that you have. The root mean squared is a little bit different, but similar. So the root mean squared error, RMSE, is very commonly used to evaluate model performance. So you have a column of P's, a column of O's, and a third column where you take the P minus I in that row and then square that value. You have to sum up all the values in that column, divide by the number of observations, and then take the square root of the whole thing. The standard deviation, I put that in there just because it has a very similar format to root mean squared error. The standard deviation equation expresses the variation about the mean of the x of I. So the root mean squared error is the variation of the predicted values compared to the observations. So the bigger the root mean square error, the bigger the variation of the predicted values compared to the observations. Well, I appreciate you your time and listening to all my lectures. It's been fun to be a guest lecturer for the lab and for the class. And when we get back together at CSU, when we're all together in person, my office is in NESB, second floor. If you happen to see me in the hall or pass by my office, please stop in and say hi and let me know how the class went for you. So good luck with the rest of the semester and good luck with your homework. I wish you well.